7.04 feet for the distance.
7.04 feet? Okay, that's certainly possible. We were about 2 feet off last year too. And it definitely has to do with the ability or inability of people to hit the start and stop button on a stopwatch at the right moment. All right, I'm going to talk through the data. We collected all 13 of these points of data in seconds to see how long it took a ball to fall from the ceiling to the floor, thanks to Chris, who is tall enough to reach the ceiling on a chair. And we measured with a measuring tape that it's 9 feet 6 inches from the ceiling to the floor. We know in English units that gravity has an acceleration of 32 feet per second squared down. We found the average of those 13 data points to be 0.66 seconds. So make sure that you fill in on your lab sheet where it says average of 10 data points. That's going to be 0.66 seconds for us. And then we're going to use this to try to find the height from which you dropped the ball. So it sounds like some of you have been working on that. Chris?
I have, did they get like 7 something?
Yes.
I have 10.56.
That's good.
Is that
all right,
right?
so let's see what we get if we plug in the numbers. I might have to find a new pen here. So we know our equation for this is going to be distance equals 1/2 times acceleration, which is 32 feet per second squared down, times time squared. So if our time average is 0.66 seconds, then we're going to square that number. So
0.4356.
okay, so what I do with this calculator, and everyone's might be different, is I go 0.66 times 0.66 times 32 divided by 2. And I get something completely different than what you guys got, so that's kind of scary. 0.66 times 0.66 times 32 divided by 2. So I get about 7 feet. I get 6.9696 feet, which
That's what I got.
is 7.0 feet. Now we know from measuring the ceiling height that it's 9 feet 6 inches. So just like last year's data, we're about 2 feet off because I think we just aren't able to hit the stopwatch fast enough for that short distance. If we could do it for a longer distance, our error would be less. But it's just a demonstration of how you might calculate time using a stopwatch instead of, distance using a stopwatch instead of a ruler. We're also supposed to do the math in meters on this sheet, so we need to figure out what that would be in meters. So all I have to do for that is just change the, I give up. I have new pens somewhere, hold on. You just have to change the acceleration number from 32 feet per second squared down to 9.8 meters per second squared down. Here we go. Yes.
Whoop whoop.
So, everyone try to calculate the distance in meters instead of in feet now.
I felt like she told us to do stop it, and I forgot.
Hi. Yeah, I got 2.13444.
That too. I have a very limited one.
And what did you get, Lily?
I got 2.13444.
2.13 meters.
I got 3.234 meters.
Okay, so let's type it in. 0.66 times 0.66
We did the same thing.
What?
times
Same thing.
9.8.
I did the same thing.
Yeah, I get 2.13, which is that. Anyone else want to try? 2.13 meters? Okay, so in meters right here, we get 2.13 meters. In feet, we get 7.0 feet. We know that the ceiling is 9 feet 6 inches high. So we need to calculate our percent error. That's here. It says measure the height and compare the two answers. Write the calculation for percent error. So we're only going to calculate percent error for 7.0 feet because we measured the height with a tape measure that only measures feet. So here's how you do percent error, something you probably haven't done before. So percent error equals the known value minus the experimental value divided by the known value. And then you take the absolute value of that. Who has not ever seen absolute value in math? So what absolute value technically means in math is the distance that something is from 0 on a number line. So the absolute value of, for example, the number 6 and the absolute value of the number -6 are exactly the same because they're both 6 units from 0 on the number line. What it means in all practical purposes for us is that if we get a negative answer, we can ignore the fact that it's negative and just make it positive. Okay, so then you multiply by 100%. So our known answer, so which answer are we more confident about? The answer where we measured with a measuring tape or the answer where we measured with a stopwatch?
Measuring tape.
The measuring tape, yes. So we're going to plug in the measuring tape answer for the known, which is 9.5 feet. 9 feet 6 inches is 9.5 feet. And minus the experimental, which is 7.0 feet, divided by the known, which is 9.5 feet. And that ends up being a positive number, so we don't have to worry about absolute value in this case. Then we just multiply by 100%, and we get the answer. So if you type, and you don't need to know how to do percent error for the test. It's just something that is important for this lab because I was pretty confident we were going to have a large amount of error.
Oh, great.
So what do we get? If you do 9.5 minus 7 divided by 9.5 times 100.
I got 25.9.
Okay, I got 26.3, so something around there, 25 or 26%.
Wait a second.
So that means that we're, 26% off of the real answer. But considering we measured distance with a stopwatch, that's at least interesting, not wonderful. 10% error is kind of best case scenario for labs that we can do without specialized equipment. So, now that we've kind of talked through that, why did we bother to do 10 trials? Why didn't we just have him drop the ball once and get off the chair? Chris?
So we had less chance of error. Like we were going to do that many times. You probably could have gotten one correct or something like that.
Didn't you
Sort
lower
of.
the effects of experimental error because you have lots of information?
Okay, so we could say 13 measurements. Were taken instead of 1 to reduce the effects of experimental error. So if we had only done done it one time, what if I had just clicked the button wrong? What if I'd been way off? Would we have ever known that?
No.
What if I had just lied and picked an answer that I knew would give us 9.5 feet? Right? If we only take one data point, then we have no idea, nothing to compare it to, no way to know if we're anywhere near right. If my reflexes are terrible, maybe you young folks have faster reflexes than I do, better at the stopwatch, then the data I report can't be trusted. Or the data someone with slow reflexes reports, in this case, can't be trusted. So we took lots of data points because perhaps sometimes somebody's finger didn't hit the button in time. Maybe sometimes some people anticipated and hit it too soon. And, that is something that's easy to do for humans. So when we average lots of data points, hopefully the ones that are way too small or way too big cancel each other out. That's kind of the goal. So, points that are much too small or large. So would it be better to have taken 100 data points than 10? Yes. But there has to come a point when you are realistic about things, and 10 is good enough.
It'd be a really long problem.
It would, and in college you may have those moments when you get to repeat many times more than you think is necessary, but that's the way it goes, and it does reduce error. But you have to think, how much do I really need this to be reduced?
After a while, you just start just.
And that
punch the
can
button.
happen too. Yeah, just push the button.
So
and
10 is probably-
merp. It only takes this long, merp, and it doesn't mean anything anymore. Also in college, you'll find that you have electronic equipment that collects your data much more accurately than you ever could. So you won't have to hit the stopwatch button yourself, probably after you're done with high school.
You probably have a robot that drops the ball and
Then
then
a
a
pressure plate.
And a pressure plate.
That,
It absolutely will definitely.
if you have to
even
have
I had
that
in college.
precision, then that's probably
Then we'd probably have gotten 9.5.
rocket
feet.
scientists.
Right, we can't make ridiculous 26% error things when we're shooting, military missiles or trying to land on the moon. Obviously, we'd never accomplish anything with this kind of error. We've got to do better. So reducing experimental error is very important. So the last question is, what are the sources of error that we had? What's the biggest one, do you think?
Not hitting the stopwatch.
Yeah,
Like
timing on the
reflexes.
stopwatch, reflexes that aren't fast enough for the time it takes. I mean, really, that's a very short amount of time. Our reflexes aren't really that good. By the time we see it, hit the button, it hits the ground, we hit the button, we've got a lot of error. And Patrick, you told us about the other source of error that might affect this experiment. Is that ball truly in free fall?
Yes. Well, in a room, there's a lot less, no wind.
But there is air. So is the ball truly in free fall?
No.
No.
But-
We're ignoring air resistance, but air resistance is present, and we ignored it.
Would
so.
air resistance be more of a important problem like in college or something like that?
Yes, and in fact, you may use vacuum chambers for some things if you really want to get rid of air resistance.
Vacuum
It's
chamber in
possible.
space.
Space that is
Actually, no, they have a
right
giant
here.
vacuum chamber that's like
So.
3 stories high. It's huge. They test spaceships in there.
So air resistance is a smaller source of error than the stopwatch problem, but it still exists. It slows that ball down so that when gravity is not the only force acting on the ball, but it's the only force we're considering, there is some error going on there. So air resistance on the ball is the other source of error. So now I'm going to stop the camera if it didn't already die, because
No, it's still going.
we're going to do